In the summer of 2012, the Mars rover Curiosity was making its careful way across the rust-colored surface of Gale Crater, when mission controllers spotted something extraordinary. Dark streaks were appearing on nearby slopes, flowing downhill during the Martian summer and fading in winter. They looked suspiciously like water, liquid water, trickling down the face of Mars. It was exactly the kind of discovery that Curiosity had been built to investigate, the kind of finding that could rewrite our understanding of the red planet. So naturally, NASA did the only logical thing. They told Curiosity to stay the hell away from it. Not because the rover might get stuck or damaged, not because the terrain was too difficult to navigate, but because of a treaty signed in 1967 by people who had never built a Mars rover, never seen these dark streaks, and most of whom are now dead. Welcome to the fascinating and frustrating world of planetary protection, where the most interesting places in the solar system are the ones we're explicitly forbidden from visiting. Space, as it turns out, has boundaries. Not the kind imposed by physics or engineering limitations, though we'll get to those later. These are boundaries we've drawn ourselves, invisible lines in the cosmos that our spacecraft are not allowed to cross. Some of these forbidden zones exist to protect potential alien life from us. Others exist to protect us from potential alien life. Still others are off-limits because of politics, military secrecy, or simply because the environment is so hostile that our best technology would be destroyed in seconds. And a few places are forbidden because the laws of physics themselves become problematic, where our equations break down and reality gets weird. This is the story of every place in space we're not allowed to go, and more importantly, why we decided to put up the keep out signs in the first place. The whole mess started in the 1960s, when humanity was just beginning to figure out how to throw objects at other planets with any degree of accuracy. The Soviet Union had successfully crashed several probes into Venus and Mars, while the Americans were planning increasingly ambitious missions to land gently and actually look around. But then, someone asked an uncomfortable question. What if we accidentally contaminate Mars with Earth bacteria? And, more unsettling, what if we bring something back? The concern wasn't entirely hypothetical. We knew that some microorganisms could survive in extreme environments. Tardigrades, those microscopic water bears that look like vacuum cleaners designed by someone on hallucinogens, can survive in the vacuum of space. Certain bacteria form spores that can withstand radiation, extreme temperatures, and desiccation for years. What if we inadvertently seed Mars with terrestrial life, and then decades later discover Martian microbes that turn out to be Earth bacteria we brought there ourselves? We'd be in the awkward position of having discovered extraterrestrial life that we had placed there, like hiding Easter eggs and then acting surprised when we find them. Even worse, what if Martian organisms turn out to be biologically compatible with Earth life? The scenario sounds like bad science fiction, but when the Apollo 11 astronauts returned from the Moon, they were quarantined for 3 weeks. Not because anyone seriously thought moon germs would wipe out humanity, but because no one could be absolutely certain they wouldn't. Neil Armstrong, Buzz Aldrin, and Michael Collins spent their first weeks back on Earth inside a modified Airstream trailer, just in case they'd brought back lunar plague. Spoiler alert, they hadn't. The Moon is sterile, baked by radiation, and utterly devoid of water. But Mars might be different. So, in 1967, while the space race was in full swing and the United States and Soviet Union could barely agree on what day of the week it was, they managed to come together with other spacefaring nations to sign the Outer Space Treaty. It's a remarkably brief document, especially considering it's meant to govern all human activity in the infinite cosmos. Most of it deals with preventing the weaponization of space and ensuring that no country can claim the moon as sovereign territory. But buried in Article 9 is this critical passage. States parties to the treaty shall pursue studies of outer space, including the moon and other celestial bodies, and conduct exploration of them so as to avoid their harmful contamination and also adverse changes in the environment of the Earth resulting from the introduction of extraterrestrial matter. It's remarkably vague, of course. What counts as harmful contamination? How much caution is reasonable? The treaty doesn't say. It just establishes the principle that we should probably try not to contaminate other worlds or bring back anything that might contaminate ours. To figure out the actual rules, that responsibility fell to an organization called COSPAR, the Committee on Space Research. COSPAR is exactly the kind of international scientific body you'd expect to make these decisions, composed of respected researchers who meet periodically to argue about acceptable contamination levels and then write reports that almost nobody reads. They've divided solar system bodies into 5 categories based on their scientific interest and the likelihood that they could harbor life. Category 1 includes places like the Moon and Mercury, dead worlds with no possibility of life where we can do basically whatever we want. Crash probes into them. Leave debris scattered across the surface, no problem. Category 2 covers places where there's some scientific interest but low probability of contamination affecting our research. Venus falls here, which is ironic given that its surface is hot enough to melt lead. Category 3 is for flyby and orbital missions to places like Mars, where we need to document what we're doing, but restrictions are minimal. Category 4 is where things get serious. This covers landers and rovers going to places where liquid water might exist, and it's subdivided into categories based on the target. Mars landers require extensive sterilization. Europa missions require even more. And then there's Category 5, which is for sample return missions, bringing extraterrestrial material back to Earth. Here the concern flips around. We're not worried about contaminating the target, we're worried about contaminating Earth. The strange thing about planetary protection is that we're simultaneously trying to accomplish 2 contradictory goals. On one hand, we want to protect potential alien biospheres from Earth life, preserving them in their pristine state for scientific study. And, because it would be ethically questionable to accidentally cause the first interplanetary extinction event. On the other hand, we want to protect Earth's biosphere from potential alien contamination, just in case Mars harbors organisms that view humans the way we view a convenient buffet. It's worth noting that the latter concern is almost certainly paranoid. The odds of Martian microbes being biologically compatible enough with Earth life to actually infect us are vanishingly small. We share common ancestry with every organism on Earth, and we still can't catch Dutch elm disease or wheat rust. The idea that a microorganism that evolved independently on Mars would find human cells a welcoming environment is like assuming that someone who's only ever eaten Japanese food could seamlessly transition to servicing Volkswagens. The skills don't transfer, but almost certainly isn't the same as absolutely certainly. So, Category 5 missions require approved containment protocols. When the Apollo astronauts returned with moon rocks, those samples spent time in isolation. Future Mars sample return missions will require even more elaborate procedures. The material will be contained in multiple layers of protection, studied in specialized facilities, and probably subjected to more security theater than a presidential motorcade. All of this seems perfectly reasonable until you realize what it means in practice. The most scientifically valuable locations, the places where we're most likely to find evidence of life, are the places where our robots aren't allowed to go. Take Mars, for example. The red planet, humanity's favorite target for exploration and future colonization, is absolutely lousy with restrictions. COSPAR has designated certain areas as special regions, defined as places where liquid water could potentially exist and where Earth microorganisms could potentially replicate. These regions are based on two parameters: temperature above -43 degrees Celsius and water activity above 0.5. In less technical terms, if it's warm enough and wet enough that terrestrial bacteria might survive, it's off limits unless your spacecraft has been sterilized to an extraordinary degree. Now, you might be thinking, Mars is a frozen desert. How many places could possibly meet those criteria? The answer is, we're not entirely sure, and that uncertainty is part of the problem. We know that Mars has water ice at the poles and in subsurface deposits. We know that the thin Martian atmosphere creates temperature variations, and we know that under certain conditions, liquid water can briefly exist on the surface despite the low atmospheric pressure. But the details are fuzzy. This brings us back to those dark streaks that Curiosity spotted, features known as recurring slope lineae, or RSL, for those who prefer their planetary mysteries in acronym form. These dark lines appear on Martian slopes during warm seasons and fade during cold ones. They flow downhill, following the contours of the terrain. For years, the leading hypothesis was that they were caused by briny water, salty enough to remain liquid at Martian temperatures, seeping from subsurface sources. If that hypothesis was correct, RSL would be exactly the kind of place where Martian life might exist, sheltered from radiation, with access to liquid water. They would also be exactly the kind of place that Curiosity was forbidden from approaching. The irony is exquisite. We sent a $2.5 billion rover to Mars specifically to search for conditions that could support life, equipped it with sophisticated instruments to analyze soil and rock samples, and then discovered that the most promising targets are legally off-limits. It's like booking an expensive safari to see lions, and then being told you have to stay at the hotel because you might disturb the lions. Now, the story has gotten more complicated since then. More recent research suggests that RSL might not be caused by liquid water after all, but rather by granular flows of dry dust and sand. If that's true, they wouldn't qualify as special regions, and rovers could investigate them freely. But the debate illustrates the fundamental problem with planetary protection. We're making rules about places we don't understand, using criteria that might not even be relevant, all in service of protecting life that might not exist. And yet, despite all the frustration, the restrictions make sense. Because if there is life on Mars, even just microbial life clinging to existence in subsurface brine deposits, the scientific value of that discovery would be incalculable. It would answer one of humanity's oldest questions: are we alone? Finding Earth bacteria that we accidentally brought to Mars would answer exactly nothing. So we sterilize our spacecraft. NASA's clean rooms, where Mars rovers are assembled, are maintained at class 10,000 or better, meaning there are fewer than 10,000 particles larger than 0.5 microns per cubic foot of air. Workers wear full body suits that make them look like budget astronauts. Every component that will travel to Mars is carefully cleaned, and many are baked in ovens to kill any lingering microorganisms. the entire spacecraft might be heated to 110 degrees Celsius for 30 hours. It's not quite enough to guarantee absolute sterility. That would require temperatures that would destroy the electronics, but it reduces the bioburden to acceptable levels. The accepted standard for Mars landers is 300,000 bacterial spores on the external surfaces and 300 spores on any components that might contact special regions. To put that in perspective, your kitchen sponge contains about 10 billion bacteria. We're talking about cleaning a rover to a level of sterility that would make an operating room look filthy by comparison. When Perseverance launched in 2020, it carried the Ingenuity helicopter, the first aircraft to fly on another planet. That little drone required its own special sterilization protocols because it was going to touch Martian soil repeatedly and kick up dust with its rotors. The engineering team had to figure out how to bake a helicopter without melting its electronics or compromising its lightweight structure. They succeeded, and Ingenuity has now completed dozens of flights, proving that Martian aviation is possible and that planetary protection doesn't have to ground our ambitions. But the restrictions raise an uncomfortable question for the future. What happens when humans want to land in special regions? People are absolutely lousy at being sterile. We're walking bacterial ecosystems, shedding skin cells and microorganisms wherever we go. The average human body contains about 30 trillion human cells and roughly the same number of bacterial cells. We're not individuals, we're symbiotic colonies. When astronauts go to Mars, and they will eventually, they're going to bring their microbiome with them. We can sterilize spacesuits and equipment, but we can't sterilize the astronauts without killing them. So, either we accept that human exploration of Mars will inevitably contaminate the planet, at least to some degree, or we keep astronauts away from the most interesting locations. The first option is scientifically problematic. The second option is, well, let's just say that telling astronauts they've traveled 100 million miles but can't visit the cool spots is going to go over about as well as telling kids they can look at Disneyland from the parking lot. If Mars is complicated, Europa is a whole different level of nightmare. Europa, one of Jupiter's 4 large moons, is covered in water ice and almost certainly harbors a liquid ocean beneath its frozen crust. That ocean might contain more water than all of Earth's oceans combined, kept liquid by tidal heating as Jupiter's massive gravity flexes the moon's interior. It's one of the most promising places in the solar system to search for life, which means it's also one of the most heavily restricted. Europa is classified as Category 4, the highest level of restriction for robotic missions. But within Category 4, Europa gets special treatment. The planetary protection requirements are so stringent that they border on paranoid, and for good reason. If there's life in Europa's ocean, it's been isolated from the rest of the solar system for billions of years, evolving in complete darkness under kilometers of ice. Contaminating that environment with Earth microbes wouldn't just compromise our scientific investigation, it could potentially destroy a unique biosphere that represents an independent origin of life. The sterilization requirements are correspondingly extreme. The target is fewer than 0.0003 organisms per square meter of spacecraft surface. Let me put that in perspective. That's about 1 organism per 30 square meters. A typical spacecraft might have hundreds of square meters of surface area, so we're talking about tolerating perhaps a dozen bacteria on the entire vehicle. Achieving this level of cleanliness is almost absurdly difficult. It's not enough to bake the spacecraft, you have to do it multiple times. You have to use chemical sterilization. you have to seal components in sterile containers, and even then, you can never be absolutely certain you've eliminated every last microbe. Some bacteria form spores that can survive extreme heat and radiation. Some hide in microscopic crevices that are impossible to reach with cleaning solutions. The engineering challenge is compounded by Europa's radiation environment, which we'll discuss in more detail later. But suffice it to say that Jupiter's magnetosphere bathes Europa in enough radiation to kill a human in a matter of hours. This creates a darkly ironic situation where the radiation that makes Europa nearly impossible to explore also serves as a backup sterilization system. Any bacteria that somehow survived the cleaning process and made it to Europa's surface would be fried by radiation long before they could contaminate the subsurface ocean. Probably, unless they were in a sheltered location, or unless they were particularly radiation resistant. The uncertainty is what drives the stringent requirements. NASA's Europa Clipper mission, scheduled to arrive in the 2030s, will perform dozens of flybys of the Moon but won't land. It will study Europa's ice shell, analyze the composition of material ejected from the surface, and search for plumes of water vapor erupting from the subsurface ocean. All of this from a safe distance, threading the needle between scientific investigation and contamination risk. Future missions might land on Europa, drill through the ice, and explore the ocean directly. Those missions will require even more elaborate sterilization procedures, and they'll probably cost tens of billions of dollars. The question becomes whether the scientific return justifies the expense and effort, or whether we should focus on easier targets. But easier targets aren't necessarily better targets, and Europa remains one of the most tantalizing destinations in planetary science precisely because it's so difficult to reach and so carefully protected. Then there's Enceladus, another icy moon with a subsurface ocean, this one orbiting Saturn. Enceladus is in some ways even more intriguing than Europa because it's actively venting material from its ocean into space through massive plumes at its south pole. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition and confirming the presence of liquid water, organic molecules, and chemical energy sources. Everything you'd need for life, spraying conveniently into space where we can sample it without even landing. It's like Europa is offering home delivery. And yet, Enceladus is also heavily protected under planetary protection protocols. The plumes make it easy to study the ocean, but they also create a direct pathway for contamination. If a spacecraft carrying Earth microbes crashed into Enceladus, particularly near the South Pole, there's a non-zero chance that some of those microbes could make their way into the subsurface ocean. Unlikely, perhaps, but not impossible. So Enceladus is restricted, even though studying it would be easier than studying Europa. Then there's Titan, Saturn's largest moon, which occupies a strange middle ground in planetary protection debates. Titan has liquid on its surface, but it's not water. It's liquid methane and ethane at minus 179 degrees Celsius. The surface is far too cold for life as we know it. However, Titan's subsurface might harbor a water ocean like Europa and Enceladus, and its surface is rich in complex organic chemistry. Some researchers argue that Titan could host exotic life based on liquid hydrocarbons rather than water. Others argue that this is speculative, and that Titan should be more accessible for exploration. The debate continues, but for now, Titan remains partially restricted. The fundamental question underlying all of planetary protection is this: should we prioritize scientific investigation or preservation? If we could definitively prove that Mars has no life, we could explore it freely without worrying about contamination. But we can't prove that without exploring it, which we can't do freely because we might contaminate it. It's a circular problem with no clean solution. Some scientists argue that we're being too cautious, that the restrictions are based on worst-case scenarios, and that the actual risk of harmful contamination is minimal. They point out that Mars and Earth have been exchanging material via meteorites for billions of years. Every time a large asteroid hits Mars, it blasts rocks into space, some of which eventually fall to Earth as Martian meteorites. Similarly, Earth rocks have been landing on Mars for eons. If Earth life could survive on Mars, it's probably already there. Others argue that we're not being cautious enough, that the discovery of even simple, microbial life beyond Earth would be so profound that any risk of contamination is unacceptable. They point out that natural exchange of material between planets is rare, and that the rocks that survive the journey are the ones least likely to carry viable microorganisms. Deliberately sending spacecraft is different. Both sides have valid points, and the truth probably lies somewhere in the middle. But the middle is a hard place to locate when you are writing regulations that will govern missions costing billions of dollars. So we do our best, we sterilize our spacecraft, we designate special regions, and we send our robots to the places where they're allowed to go, while the most interesting locations remain tantalizingly out of reach. For now. While planetary protection keeps us away from certain worlds for ethical and scientific reasons, there are places in space where the universe itself has posted keep-out signs. These are regions where the laws of physics become actively hostile to our presence, where radiation levels climb so high that electronics fail and metal corrodes, where temperatures exceed anything we can shield against, and where the very fabric of space is so warped that our equations start giving nonsensical answers. These aren't places we've chosen to avoid. These are places where nature has made the choice for us, at least with current technology. And the most surprising thing is that some of these deadly zones are remarkably close to home. In fact, you're inside one of them right now. On January 31st, 1958, the United States successfully launched Explorer-1, the first American satellite to reach orbit. It was a response to the Soviet Union's Sputnik, a frantic attempt to prove that America could also reach space. The satellite itself was remarkably simple, basically a tube packed with instruments and powered by batteries that would last a few months at best. One of those instruments was a Geiger counter designed by physicist James Van Allen to measure cosmic radiation. Van Allen expected the counter to detect a relatively constant level of radiation, maybe with some variation based on the satellite's position. What he got instead was complete chaos. Sometimes the Geiger counter would click away normally, detecting the expected background radiation. But at certain points in the orbit, the counter would go completely silent. At first, Van Allen thought the instrument had failed. But then he realized what was happening. The counter wasn't broken, it was overwhelmed. The radiation levels were so high that the instrument was saturating, unable to keep up with the particle flux. It was like trying to count raindrops in a hurricane. Van Allen had discovered that Earth is surrounded by two massive donuts of trapped radiation, zones where charged particles from the solar wind get captured by our planet's magnetic field and spiral back and forth between the poles. These belts, which were quickly named after him, extend from a few hundred kilometers above Earth's surface to more than 60,000 kilometers out. The inner Van Allen belt, sitting roughly between 1,000 and 6,000 kilometers altitude, is composed primarily of high-energy protons. These are the dangerous ones, particles moving fast enough to penetrate shielding and damage both electronics and biological tissue. The outer belt, extending from about 13,000 to 60,000 kilometers, contains mostly electrons. Less immediately dangerous than protons, but still capable of causing significant problems over time. The intensity of radiation in these belts is difficult to overstate. In the heart of the inner belt, a human without shielding would receive a lethal dose in a matter of minutes. Satellites passing through experience constant bombardment by particles that can gradually degrade solar panels, corrupt computer memory, and induce electrical currents in sensitive components. This is why the International Space Station orbits at only 400 kilometers altitude, safely below the inner belt. It's why most satellites occupy either low Earth orbit, below the belts, or geosynchronous orbit, far above them. The belts themselves are essentially a no man's land, a zone you pass through as quickly as possible but never linger in. The Apollo astronauts who traveled to the moon had to pass through the Van Allen belts, a fact that conspiracy theorists love to point out as evidence that the moon landings were faked. How could the astronauts survive such intense radiation? The answer is actually quite straightforward. They went through it really fast. The Apollo spacecraft spent less than an hour passing through the belts on the way to the moon, and the trajectory was carefully planned to avoid the most intense regions. The total radiation dose received by the Apollo crews from passing through the Van Allen belts was roughly equivalent to a chest X-ray. Unpleasant if you're getting a lot of them, but hardly lethal. The difference between passing through quickly and lingering is the difference between running across hot coals and standing on them. One is survivable with minor discomfort, the other is catastrophic. But even Earth's radiation belts have nothing on the real hazard zones in the solar system. If you want to see where radiation becomes truly apocalyptic, you have to travel to Jupiter. Jupiter's magnetosphere, the region of space dominated by its magnetic field, is absolutely monstrous. It extends more than 7 million kilometers toward the Sun and stretches behind the planet in a tail that reaches all the way to Saturn's orbit. If you could see Jupiter's magnetosphere from Earth, it would appear larger than the full moon despite being roughly 2,000 times farther away. This isn't just a scaled-up version of Earth's magnetic field. Jupiter's magnetosphere is 20,000 times stronger than Earth's, and that difference makes for a qualitatively different environment. The radiation belts around Jupiter don't just trap particles from the solar wind. They create their own through a process involving Io, the innermost of Jupiter's large moons. Io is the most volcanically active body in the solar system, spewing sulfur and oxygen into space at a rate of about 1 ton per second. These particles get ionized by sunlight and Jupiter's radiation, stripped of their electrons and turned into plasma. Jupiter's rapid rotation, a day on Jupiter, is less than 10 hours long, then accelerates this plasma to incredible speeds, creating a particle accelerator the size of a planet. The result is a radiation environment so intense that it defies comprehension. In the heart of Jupiter's radiation belts, the particle flux is millions of times higher than in Earth's belts. A human exposed to this environment would receive a fatal dose in less than a second. Not hours, not minutes, but literally faster than you could say the word radiation. Europa, that tantalizing, icy moon we discussed earlier, orbits directly through Jupiter's radiation belts. The surface of Europa receives a radiation dose of about 5.4 sieverts per day. To put that in perspective, a whole-body dose of 5 sieverts delivered all at once is lethal to roughly half of humans who receive it. Europa gets that much every single day, continuously, forever. If you were standing on Europa's surface without shielding, you'd be dead before you could finish admiring the view. This creates a unique problem for mission planners. Not only do you have to sterilize spacecraft going to Europa to prevent contamination, you have to build them to survive an environment that's actively trying to destroy them. Electronics fail under radiation exposure through several different mechanisms, all of which have wonderfully technical names that obscure how terrifying they actually are. Single event upsets occur when a single high-energy particle strikes a computer chip and flips a bit in memory, changing a 0 to a 1 or vice versa. Most of the time this is harmless, the computer notices the error and corrects it. But occasionally it happens at exactly the wrong moment, corrupting critical data or instructions. Single event latch-up is worse. This happens when a particle strike creates a short circuit in a chip, causing it to draw excessive current. If not detected and corrected quickly, the chip can overheat and permanently fail. And then there's total ionizing dose, the cumulative effect of radiation exposure over time. Even if individual particle strikes don't cause immediate damage, the gradual accumulation of radiation can degrade materials, cause insulation to break down, and eventually render electronics completely inoperable. NASA's Juno spacecraft, currently orbiting Jupiter, was specifically designed to survive this hellish environment. Its most critical electronics are housed in a titanium vault, a heavily shielded box about the size of a car's trunk that reduces radiation exposure by a factor of 800. Even with this protection, Juno's computer is expected to accumulate enough radiation damage that the mission has a limited lifespan. The spacecraft follows a highly elliptical orbit, swooping close to Jupiter for a few hours to collect data, then retreating to a safer distance for the rest of its 53-day orbit. It's like a boxer who darts in to land a punch and immediately retreats before the opponent can counter. Even so, Juno is accumulating damage with every pass. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provides a cautionary tale about what happens when you spend too long in Jupiter's radiation environment. Galileo was supposed to last 2 years. It survived for 8, far exceeding its design lifetime, but those extra years came at a cost. The spacecraft's camera began developing increasing numbers of stuck pixels as radiation damaged its electronics. The onboard tape recorder, used to store data between transmissions to Earth, started experiencing errors. Eventually, multiple systems began failing simultaneously. When NASA deliberately crashed Galileo into Jupiter in 2003, to prevent it from potentially contaminating Europa, the spacecraft was held together more by hope than by functional hardware. Future missions to the Jupiter system will have to grapple with these same constraints. The proposed Europa Clipper mission will use a similar strategy to Juno, making brief, close passes of Europa and then retreating to safer distances. A mission to actually land on Europa and drill through the ice to reach the subsurface ocean would require either dramatically better radiation shielding or acceptance that it would be a short-lived mission. Some engineers have proposed using the ice itself as shielding, landing a probe and then drilling down several meters before deploying sensitive instruments. Water ice is actually quite good at blocking radiation, which is why Europa's subsurface ocean is potentially habitable despite the hellish radiation at the surface. But this approach creates its own engineering challenges. you'd need a drill capable of operating in minus 170-degree temperatures, and you'd need to do it with a spacecraft small enough and light enough to actually reach Europa in the first place. Every kilogram of mass you add to a spacecraft requires more fuel to accelerate it, which requires a larger rocket, which costs more money. The trade-offs become brutal very quickly, and even if you solve all these problems, you still have to ask whether the scientific return justifies the cost and risk. A mission to Europa might cost $5 billion or more. For that same amount of money, you could launch dozens of smaller missions to less challenging targets. This is the tyranny of radiation belts. They don't make exploration impossible, but they make it expensive and difficult enough that we have to very carefully consider whether it's worth the effort. If you thought Jupiter's radiation was bad, try getting close to the Sun. The Sun is not, strictly speaking, surrounded by radiation belts in the same way that planets are. Instead, the Sun itself is the source of radiation, continuously ejecting particles in all directions in the form of the solar wind. Getting close to the Sun means exposing yourself to increasingly intense radiation, extreme temperatures, and the very real possibility of being hit by a coronal mass ejection, an explosive burst of plasma that makes Jupiter's radiation belts look quaint by comparison. NASA's Parker Solar Probe, launched in 2018, currently holds the record for closest approach to the Sun. On its closest passes, Parker gets within about 4.3 million miles of the solar surface. That might sound like a safe distance. It's roughly 18 times farther than the Moon is from Earth, but in the context of solar observation, it's insanely close. No previous spacecraft had gotten within about 27 million miles. Parker is essentially skimming the Sun's outer atmosphere, the corona, flying through plasma that's been heated to millions of degrees. And here's where things get weird. The corona has a temperature of around 1 million degrees Celsius. The surface of the Sun, the photosphere, is about 5,500 degrees. The corona is hotter than the surface, which violates our everyday intuition about how heat works. You don't normally move away from a fire and find that the air gets hotter. This temperature inversion is one of the great mysteries of solar physics, and Parker is trying to solve it. But temperature and heat are not the same thing, a distinction that becomes crucial to understanding how Parker survives. Temperature is a measure of how fast particles are moving. Heat is a measure of total energy transfer. The corona is incredibly hot because the particles in it are moving incredibly fast, but it's also incredibly sparse. There just aren't that many particles. It's like the difference between sticking your hand in a conventional oven at 200 degrees and sticking your hand in a blast furnace at 200 degrees. The oven and the furnace are the same temperature, but the blast furnace contains far more mass at that temperature, so it can transfer far more heat to your hand, burning you much more quickly. The corona is hot but not dense, so the total amount of heat it can transfer to the Parker Solar Probe is manageable. Manageable, but still extreme. The probe's heat shield, officially called the Thermal Protection System, is a slab of carbon-carbon composite foam about 4.5 inches thick. It's the same material used on the leading edges of the Space Shuttle's wings, chosen because it can withstand temperatures up to about 1,400 degrees Celsius without degrading. Behind this shield, the spacecraft remains at a relatively comfortable room temperature. The gradient is absurd. One side of the heat shield is hot enough to melt steel, while the other side is cool enough that a human could touch it. Parker also has to deal with the Sun's intense radiation, both electromagnetic and particle. The spacecraft's solar panels are actively cooled and can retract behind the heat shield during close approaches. Its instruments peek out from behind the shield to make measurements, then quickly duck back into cover. Despite all these precautions, Parker is still accumulating damage. Each close pass subjects the spacecraft to extreme thermal stress, and over time, this takes a toll. The mission is planned for 7 years and 24 close approaches, and by the end, the spacecraft will likely be barely functional. So, how close could we actually get to the Sun? The answer depends on what you're trying to accomplish and how long you want to survive. If you're willing to accept a one-way suicide mission, you could potentially build a probe that could get much closer than Parker, maybe within 1,000,000 miles or even less. But you'd need better heat shielding, probably multiple layers with active cooling, and you'd have to accept that the mission would last minutes at most. Your probe would take measurements, transmit data back to Earth, and then melt. For a crewed mission, the constraints become far more severe. Humans require life support, which means pumps, filters, and electronics that can't be turned off. They require more mass for shielding, food, water, and oxygen. And they require a way to get back, which means a return trajectory and fuel. A human mission to the inner solar system, getting significantly closer to the Sun than Mercury, is theoretically possible, but would require technology we don't currently have. Advanced heat shields, possibly using active cooling with liquid metal. Extremely efficient power systems to run all that cooling, and probably some form of magnetic shielding to deflect charged particles. We're talking about technology that exists mainly in concept papers and optimistic PowerPoint presentations. As for actually touching the Sun, landing on its surface the way we landed on the Moon, that's not merely difficult, it's definitionally impossible. The Sun doesn't have a solid surface. It's a ball of plasma, ionized gas held together by gravity. As you descend into the Sun, the density gradually increases, but there's no discrete boundary where gas becomes solid. Eventually, you reach the core, where temperatures hit 15 million degrees and pressure reaches 250 billion times Earth's atmospheric pressure. At that point, the distinction between your spacecraft and the surrounding plasma becomes moot, because your spacecraft is now also plasma. If radiation and heat weren't enough, space also conspires against us through the subtle tyranny of orbital mechanics. There are certain points in space where the gravitational forces of two large bodies perfectly balance, creating regions of stability where objects tend to accumulate. These are called Lagrange points, named after the Italian-French mathematician Joseph Louis Lagrange, who calculated their positions in the 1700s. For any two-body system, there are 5 Lagrange points. 3 of them, L1, L2, and L3, lie along the line connecting the two bodies. The other 2, L4 and L5, form equilateral triangles with the two bodies. L4 leads one of the bodies in its orbit, while L5 trails behind. These points are gravitationally stable or semi-stable, meaning that objects placed there will tend to stay there without requiring much fuel to maintain position. This makes them extremely valuable for spacecraft. The James Webb Space Telescope, for instance, orbits the L2 point of the Earth-Sun system, about 1,000,000 miles from Earth in the direction away from the Sun. From this vantage point, Webb can observe the universe with Earth, Moon, and Sun all in the same direction, allowing its sun shield to block light and heat from all 3 simultaneously. It's a brilliant piece of orbital engineering, and Webb will likely remain at L2 for decades. But here's the problem. Webb isn't alone there. L2 is also home to several defunct spacecraft, satellites that have reached the end of their operational lives and were parked there because it's easier than bringing them back to Earth or sending them into solar orbit. The Wilkinson Microwave Anisotropy Probe, WMAP, which mapped the cosmic microwave background radiation from 2001 to 2010, is still hanging around L2. So is the Herschel Space Observatory and several other retired missions. These spacecraft are now space junk, and they're accumulating at a point where we want to put future telescopes and observatories. The problem isn't critical yet. L2 is a region, not a point, and there's enough space that the risk of collision is currently minimal. But as we launch more missions to L2, and we will because it's such a valuable location, the clutter will increase. Eventually, we'll need to start thinking about cleaning up, which is far easier said than done. The L4 and L5 points are even more interesting from a debris perspective. Unlike L1, L2, and L3, which are only semi-stable, L4 and L5 are genuinely stable. An object placed at L4 or L5 will naturally tend to remain there, held in place by the gravitational forces of the two larger bodies. This makes them natural collection points for debris. In the Earth-Moon system, the L4 and L5 points contain clouds of dust. In the Sun-Jupiter system, they contain asteroids, hundreds of them, trapped in gravitationally stable orbits leading and trailing Jupiter. These asteroid groups are called the Greek and Trojan camps, named after characters from the Iliad, because apparently astronomers in the early 1900s were really into classical literature. The existence of these asteroid clouds demonstrates what happens when you have stable gravitational points and billions of years for stuff to accumulate. They fill up. Now, transfer this concept to Earth orbit, where we're launching thousands of satellites, and you can see the potential problem. As more satellites are placed at or near the L4 and L5 points of the Earth-Moon system, those regions will gradually become more crowded. And unlike satellites in low Earth orbit, which eventually decay and burn up in the atmosphere, objects at Lagrange points can remain there essentially forever, unless something actively moves them. This brings us to the Kessler syndrome, a nightmare scenario first described by NASA scientist Donald Kessler in 1978. The basic idea is that as the density of objects in orbit increases, the probability of collisions also increases. When two objects collide, they don't just bounce off each other. They shatter into hundreds or thousands of fragments, each of which is now a projectile traveling at orbital velocity. These fragments can then collide with other objects, creating more fragments in a cascading chain reaction. Eventually, you reach a point where certain orbital regions become so filled with debris that it's effectively impossible to operate there without your spacecraft being destroyed. We're already seeing early signs of this problem in low Earth orbit. There are currently more than 30,000 tracked objects larger than 10 centimeters in orbit, and probably millions of smaller fragments that we can't track. Several collisions have already occurred. In 2009, the defunct Russian satellite Cosmos 2251 collided with the active American satellite Iridium-33, creating thousands of debris fragments. In 2007, China conducted an anti-satellite weapons test, deliberately destroying one of their own weather satellites and creating more than 3,000 trackable fragments, plus countless smaller ones. Each of these events makes the orbital environment slightly more dangerous. Lagrange points are particularly vulnerable to this problem because they're stable. Debris at L4 or L5 won't gradually decay and fall back to Earth. It'll just sit there, potentially for geological timescales, making the region increasingly hazardous. The L1 point, ironically, is relatively clean precisely because it's unstable. Objects at L1 require active station keeping, small periodic thruster burns to maintain position. If a satellite at L1 fails and can no longer make these corrections, it will drift away. It won't stay there cluttering up the space. Several proposals have been floated for cleaning up Lagrange points and other regions of space. You could use spacecraft equipped with nets or harpoons to capture defunct satellites and drag them into disposal orbits. You could use lasers to ablate material from debris, changing its orbit enough to either make it re-enter Earth's atmosphere or send it into a less problematic trajectory. You could deploy large inflatable structures to sweep up smaller fragments. All of these ideas are technically feasible, but they're also expensive, and there's no clear economic incentive to implement them. The tragedy of the commons strikes again. Everyone benefits from clean orbital space, but no individual nation or company wants to pay for the cleanup. So the debris accumulates, and we slowly make certain regions of space less accessible, one collision at a time. It's entirely possible that by the end of this century, certain orbits and certain Lagrange points will be so contaminated with debris that they're effectively unusable. Not because the laws of physics prevent us from going there, but because we've collectively trashed the place. It would be the ultimate irony, humanity being excluded from regions of space not by radiation or heat or distance, but by our own garbage. So far, we've discussed places in space that are forbidden by biology, contamination risk, radiation, or heat. These are boundaries imposed by nature and by our own cautious scientific ethics. But there's another category of forbidden zones in space. Places that are off-limits not because of physics or planetary protection, but because of politics, military secrecy, and the messy reality of international relations. These are regions where the rules are ambiguous, where treaties have loopholes you could fly a spacecraft through, and where getting too close to the wrong satellite might be interpreted as an act of aggression. Welcome to the geopolitical nightmare of orbital territory, where the question isn't whether physics allows you to go somewhere, but whether doing so might start a war. The foundation of space law, such as it exists, is the Outer Space Treaty of 1967. We mentioned it briefly when discussing planetary protection, but it's worth examining more closely because it's a document that tries to govern all human activity in space, using fewer words than your average terms of service agreement for a mobile app. The treaty establishes several key principles. First, outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty. No country can plant a flag on the Moon and declare it theirs, the way colonial powers once claimed territory on Earth. Second, the exploration and use of outer space shall be carried out for the benefit and in the interests of all countries. It's a nice sentiment that has roughly zero enforcement mechanism. Third, and most relevant to our discussion, states shall not place nuclear weapons or weapons of mass destruction in orbit around Earth, install them on celestial bodies, or station them in outer space in any other manner. This sounds comprehensive until you realize what it doesn't say. It doesn't prohibit conventional weapons in space. It doesn't prohibit weapons that are based on Earth but target space assets. And most importantly, it includes this critical phrase about activities in space being conducted, quote, in accordance with international law, including the Charter of the United Nations, in the interest of maintaining international peace and security. That last bit about international peace and security is where things get complicated, because the UN Charter explicitly recognizes the right of self-defense. So here's the loophole. The treaty prohibits weapons of mass destruction in space but says nothing about conventional weapons. And even if we stretch the interpretation to suggest that all weapons are prohibited, nations can argue that defensive systems aren't weapons. They're protective measures, and therefore allowed under the self-defense provisions of the UN Charter. This ambiguity has been exploited by every spacefaring nation at some point. The United States, Russia, China, and India have all tested anti-satellite weapons, systems designed to destroy or disable satellites in orbit. These tests are typically justified as defensive measures, protecting national security assets from potential threats. After all, modern militaries depend heavily on satellites for communications, navigation, reconnaissance, and targeting. If those satellites are vulnerable, the argument goes, then developing the capability to defend them or to deny similar capabilities to adversaries is simply prudent. The distinction between militarization and weaponization is crucial here and often deliberately obscured. Militarization means using space for military purposes, which is completely legal under the Outer Space Treaty. The U.S. military operates hundreds of satellites for communications, GPS navigation, early warning systems, and reconnaissance. Russia, China, and other nations do the same. None of this violates the treaty. Weaponization, on the other hand, means placing actual weapons in space or developing systems specifically designed to attack space assets. This falls into a legal gray area. Anti-satellite missiles launched from Earth aren't technically in space, so do they violate the treaty? What about satellites with the capability to approach and interfere with other satellites? What about directed energy weapons that can blind or damage satellite sensors? The treaty doesn't answer these questions, and nations have been very careful not to push for clarification because ambiguity serves everyone's interests. If the rules are vague, you can claim your actions are legal while condemning similar actions by adversaries as violations. It's the geopolitical equivalent of everyone agreeing that fighting is prohibited, except in self-defense, and then each side claiming that everything they do is self-defense, while everything their opponent does is aggression. This brings us to the unwritten but very real concept of exclusion zones around military satellites. While the Outer Space Treaty doesn't establish any keep-out distances in space, nations with valuable military assets have made it very clear, through both public statements and private diplomatic channels, that they consider close approaches by other nations' satellites to be provocative and potentially hostile acts. The United States operates a constellation of reconnaissance satellites, often referred to by their code designations like KH-11 or KH-12, though the actual current designations are classified. These are essentially orbital spy cameras, capable of resolving objects on Earth's surface down to a resolution measured in centimeters. The exact capabilities are classified, but it's widely believed that modern U.S. reconnaissance satellites can read license plates from orbit, or at least get close enough that the distinction doesn't matter for most intelligence purposes. These satellites are obviously high-value assets, and the U.S. does not want other nations poking around them. In theory, space is international territory, and any nation has the right to place a satellite in any orbit. In practice, if a Chinese or Russian satellite starts maneuvering to approach a U.S. reconnaissance satellite, the Americans are going to interpret that as a hostile act and respond accordingly, How they respond is where things get interesting, because the response options are limited by the same treaty that creates the ambiguity in the first place. Russia has been particularly aggressive in testing the boundaries of acceptable proximity operations. They've launched several satellites described officially as inspector satellites, spacecraft designed to, quote, monitor other space objects. In practice, these inspectors have demonstrated the ability to approach other satellites very closely, conduct what appear to be visual inspections, and in some cases, deploy smaller sub-satellites. One Russian satellite, Cosmos 2543, approached within a few kilometers of a defunct Russian satellite in 2017, then released a smaller object that maneuvered independently. The U.S. military characterized this as testing technology that could be used for a space weapon. Russia responded that it was merely inspecting their own defunct satellite to assess its condition. Both statements could be true, of course. The technology required to inspect a satellite is essentially identical to the technology required to interfere with or destroy one. China has been equally active in demonstrating space rendezvous capabilities. The Shijian-17 satellite, launched in 2016, has conducted multiple close approaches to other satellites, including several dead Chinese satellites in the graveyard orbit above geosynchronous orbit. In at least one case, Shijian-17 appeared to use a robotic arm to grapple a defunct satellite and move it to a different orbit. China described this as a space debris removal test. Western analysts noted that the same technology could be used to grab a functioning satellite and disable it or drag it out of its operational orbit. Again, both interpretations are valid. The dual-use nature of space technology makes it nearly impossible to distinguish between peaceful scientific activities and preparations for conflict. How do nations track these satellite movements and respond to potential threats? The answer is a combination of ground-based radar, optical telescopes, and careful orbital calculations. The United States Space Force operates the Space Surveillance Network, a collection of radar and optical sensors distributed around the world that track every object in orbit larger than about 10 centimeters. When a satellite makes an unexpected maneuver, moving from its predicted orbit to a new trajectory, the system detects it within hours or days depending on the altitude and visibility. If that satellite appears to be approaching a high-value U.S. asset, alarms start going off, metaphorically speaking. The response depends on the nature and severity of the approach. If it's a distant approach, say within a few hundred kilometers, it might trigger a diplomatic protest. The U.S. might contact the operating nation through back channels and express concern about the trajectory. If the approach is closer, within tens of kilometers, the response escalates. The threatened satellite might maneuver to avoid the approach, changing its orbit to maintain distance. This is easier said than done because satellites have limited fuel for orbital maneuvers, and every maneuver shortens the satellite's operational lifetime. If you're constantly dodging other satellites, you're burning fuel that you'd rather save for maintaining your primary orbit. In extreme cases, if a satellite is determined to be an imminent threat, more aggressive options exist, though they're rarely discussed publicly. These could include electronic warfare, using radio frequency jammers or directed energy weapons to disable the threatening satellite's sensors or communications. They could include kinetic options, using ground-based anti-satellite missiles to destroy the threat. The problem with kinetic options is that they create debris fields that threaten everyone's satellites, which is why they're considered a last resort. The unwritten rules of space proximity operations have evolved through a combination of diplomatic negotiations, near misses, and occasional incidents. The general principle is that satellites should maintain a minimum separation distance, typically on the order of a few kilometers for satellites in similar orbits. Approaching closer than this without prior coordination is considered provocative. Making physical contact, even with a defunct satellite, is extremely provocative unless you've given advance notice and explanation. These rules aren't codified in any treaty. They're more like customs that have developed through practice. And, like all customs, they're subject to interpretation and violation when one side decides the strategic benefit outweighs the diplomatic cost. This ambiguity is most pronounced in geosynchronous orbit, the ring of space approximately 35,786 kilometers above Earth's equator, where satellites orbit at exactly the same rate that Earth rotates. From the ground, a satellite in geosynchronous orbit appears to hover over a fixed point, making it ideal for communications and weather monitoring. You can point your satellite dish at a specific spot in the sky and know that your target satellite will always be there. This makes geosynchronous orbit incredibly valuable real estate, and unlike most of space, it's genuinely finite. There are only so many orbital slots available before satellites start interfering with each other's signals. The International Telecommunication Union, a UN agency, is responsible for allocating these slots to different nations and operators. The process is complicated, involves years of paperwork, and operates on a use it or lose it principle. If you're allocated a slot but don't put a satellite there within a certain time frame, you can lose your claim and the slot can be reallocated to someone else. This has led to several instances of what can only be described as satellite parking disputes. In 1998, Tonga, a small island nation in the Pacific, was allocated several valuable orbital slots. Before they could launch satellites to occupy those slots, a U.S. company, Tongasat, formed a partnership with Tonga to exploit those slots commercially. Other nations cried foul, arguing that Tonga was essentially selling access to orbital positions for profit, rather than using them for legitimate telecommunications needs. The dispute highlighted the tension between the principle that space is the province of all mankind and the practical reality that orbital slots are allocated to nations who can then do with them as they please. A similar dispute occurred in 2014 when two different companies claimed rights to the same orbital slot. One had filed paperwork with the ITU first, but the other actually launched a satellite into the slot while the paperwork was still being processed. The result was a standoff, with both satellites occupying nearly the same position, and both operators insisting they had legal priority. Eventually, one satellite was moved to a slightly different position, but the incident demonstrated how fragile the orbital allocation system becomes when valuable positions are at stake. The crowding problem in geosynchronous orbit is compounded by the graveyard orbit requirement. When a satellite in GEO reaches the end of its operational life, it's supposed to use its remaining fuel to boost itself into a higher orbit, about 200 to 300 kilometers above the operational GEO belt. This graveyard orbit is where dead satellites go to. Well, not rest exactly, but at least to get out of the way of functioning satellites. The problem is that this requirement is not always followed. Some satellites run out of fuel before they can complete the maneuver. Others experience failures that prevent them from executing the final boost. And some operators, particularly in the early days of satellite operations, simply didn't bother because there was no enforcement mechanism. The result is that Geosynchronous orbit now contains hundreds of defunct satellites, some in proper graveyard orbits, others drifting through the operational belt, and all of them posing potential collision hazards. Unlike low Earth orbit, where atmospheric drag eventually brings down defunct satellites, objects in geosynchronous orbit can remain there essentially forever. We're creating a permanent debris field at one of the most valuable locations in near-Earth space, and we have no clear plan for cleaning it up. The long-term sustainability of geosynchronous orbit is now a topic of serious discussion among space agencies and satellite operators. Some have proposed active debris removal, using specialized spacecraft to capture defunct satellites and either boost them to graveyard orbits or deorbit them entirely. Others suggest that new satellites should be required to carry enough fuel for proper disposal at end of life, with financial penalties for operators who don't comply. The challenge is getting international agreement on these measures when the economic incentives push in the opposite direction. Launching extra fuel costs money, and satellite operators want to maximize profit. Without enforceable regulations, the tragedy of the commons continues. If geosynchronous orbit is complicated, the Moon is an outright political minefield. For decades after the Apollo program ended, the Moon was largely ignored. The United States had won the space race, proven they could land humans on another world, and then moved on to other priorities like the Space Shuttle and International Space Station. The Soviet Union, after losing the race to land first, eventually abandoned their lunar program. For a generation, the Moon was a dead issue, interesting to scientists but not to politicians or military planners. That's changing now. Multiple nations, including the United States, China, Russia, India, and Japan, have active lunar programs with plans for both robotic and crewed missions. The United States is leading the Artemis program, which aims to return humans to the Moon by the mid-2020s and establish a permanent presence. China and Russia have announced a partnership to build their own lunar research station, explicitly positioning it as an alternative to US-led efforts. India has successfully landed robotic probes and plans future missions. The European Space Agency is involved in multiple collaborations. Even private companies like SpaceX and Blue Origin are planning lunar missions. All of this activity raises the question that the Outer Space Treaty tried to answer but didn't quite manage. Who owns the Moon? The treaty says that no nation can claim sovereignty over the Moon, but it also says that nations can freely explore and use outer space. If you build a lunar base, do you own the land underneath it? What about the resources you extract? If you find water ice at the lunar South Pole and mine it for rocket fuel, does that ice belong to you or to all humanity? The Artemis Accords, a framework agreement signed by the United States and partner nations starting in 2020, attempts to clarify some of these questions. The Accords establish principles like transparency in lunar activities, interoperability of systems, registration of space objects, and, critically, the creation of safety zones around lunar landing sites and operational areas. These safety zones are described as necessary to prevent interference and avoid harmful contamination. But critics, particularly China and Russia, argue that they're territorial claims in all but name. If the United States establishes a safety zone around their lunar base and prohibits other nations from entering without permission, how is that functionally different from claiming sovereignty? The counter-argument is that safety zones are temporary and limited to the immediate area of operations. They're not claims of ownership, but rather traffic management to prevent accidents. If two nations are both mining resources at the lunar South Pole, they need some way to coordinate and avoid collisions between equipment and personnel. Safety zones serve that purpose. The problem is that temporary often becomes permanent. The Apollo landing sites provide an instructive example. There's been discussion for years about designating the Apollo sites as protected heritage locations, similar to UNESCO World Heritage sites on Earth. The reasoning is sound. The Apollo sites have enormous historical and scientific value. The equipment left behind, the footprints in the lunar regolith, even the flags planted by the astronauts, all of these are artifacts of humanity's first steps on another world. They should be preserved for future generations. But who has the authority to designate them as protected? The Outer Space Treaty says no nation can claim sovereignty over lunar territory, which presumably includes the ability to establish protected zones. UNESCO World Heritage designation requires that the site be within a nation's territory, which the Apollo landing sites are not. Some have proposed that the sites could be designated under the Outer Space Treaty's provisions about avoiding harmful interference, but that's a stretch. The treaty's prohibition on harmful interference refers to active operations, not permanent heritage preservation. The issue remains unresolved, and in the meantime, future lunar missions will need to navigate around the Apollo sites through voluntary cooperation rather than enforceable rules. This brings us to the lunar South Pole, which has become the focus of intense international interest. The permanently shadowed craters at the South Pole are believed to contain significant deposits of water ice, trapped in areas that never receive sunlight and where temperatures remain cold enough to preserve ice for billions of years. Water is extraordinarily valuable in space. It can be consumed by astronauts, used to grow plants, split into hydrogen and oxygen for rocket fuel, or used as radiation shielding. A lunar base with access to local water is far more sustainable than one that has to import every drop from Earth. Multiple nations are planning missions to the South Pole region. The United States Artemis program is targeting areas near the pole for its first crewed landings. China's Chang'e 7 mission, planned for the mid-2020s, will explore the pole and search for water ice. India's future missions will likely target similar regions. There are only a limited number of locations at the pole that offer both sunlight for solar power and access to permanently shadowed craters with ice deposits. This creates the potential for conflict over prime real estate. If the United States establishes a base at one of these optimal locations and declares a safety zone around it, what happens when China arrives and wants to build nearby? The question of resource ownership is even murkier. The Outer Space Treaty says that celestial bodies are not subject to national appropriation, but it doesn't explicitly address resources extracted from those bodies. In 2015, the United States passed the Commercial Space Launch Competitiveness Act, which states that U.S. citizens have the right to own and sell resources they extract from asteroids and other celestial bodies. Luxembourg passed similar legislation. These laws are based on the interpretation that while you can't own the moon, you can own the stuff you mine from it. Just like you can own fish you catch in international waters, even though you don't own the ocean. Other nations, particularly those without advanced space programs, have objected to this interpretation. They argue that lunar resources are the common heritage of mankind and should be exploited for the benefit of all nations, not just those with the technology to reach them. The debate echoes historical disputes over ocean resources, seabed mining, and Antarctic territory. The difference is that with space resources, we're arguing about ownership before any significant extraction has occurred. We're fighting over lunar water ice that no one has even confirmed exists in commercially viable quantities. It would be absurd if it weren't so predictable. This is what humans do. We spot a potential resource and immediately start bickering about who gets to exploit it. While the moon's political status is messy, but at least openly debated, there are regions of Earth orbit where even the locations of satellites are classified. The U.S. National Reconnaissance Office operates a fleet of spy satellites whose orbital parameters are deliberately kept secret or obscured. Launch times and trajectories are classified. The satellites themselves are designed to minimize their radar and optical signatures. Even their official designations are often classified, referred to only by code names or project numbers that reveal nothing about their purpose. The reasoning is straightforward. If adversaries know where your reconnaissance satellites are, they can predict when those satellites will pass overhead and take measures to hide sensitive activities. They can schedule military movements for times when they won't be observed. They can camouflage installations when a satellite is approaching. By keeping the orbital parameters secret, you force your adversaries to assume they're always under surveillance, which is almost as effective as actual constant surveillance and much cheaper. The problem is that amateur satellite trackers exist, and they're surprisingly good at finding classified satellites. Hobbyists around the world use nothing more sophisticated than telescopes, cameras, and stopwatches to observe satellites passing overhead. They share data online, calculate orbital parameters, and publish predictions about where classified satellites will appear next. Some of these amateurs have been tracking classified satellites for decades and have built up detailed catalogs of orbital data that the government would prefer remain secret. The U.S. military response to amateur satellite tracking has evolved over the years. Initially, they tried to discourage it, sometimes visiting trackers and asking them to stop publishing orbital data. That approach failed because you can't really prevent people from looking up and writing down what they see. More recently, the military has shifted to a strategy of obscurity rather than secrecy. They don't prevent people from tracking satellites, but they also don't confirm or deny the accuracy of published orbital data. They occasionally move satellites to new orbits without warning, forcing trackers to relocate them. And for the most sensitive satellites, they use stealth technology. The MISTY satellites, a series of reconnaissance spacecraft launched in the 1990s and 2000s, were reportedly designed to be difficult to detect visually and by radar. The exact details are classified, naturally, but it's believed they used a combination of dark coatings to reduce reflectivity and possibly inflatable shrouds to mask their true shape and size. Amateur trackers still found them, of course, because hiding something in orbit is fundamentally difficult. Any object in orbit is moving against the background of stars and will eventually cross in front of a telescope. But the stealth measures do make tracking more difficult and force trackers to spend more time searching. The existence of classified orbital regions raises interesting legal questions. If the Outer Space Treaty says that space is the province of all mankind and that space activities should be conducted with transparency, is it legal to operate satellites in secret orbits? The answer appears to be yes, as long as you're not violating other provisions of the treaty. Operating a reconnaissance satellite doesn't violate the treaty's prohibition on weapons of mass destruction. It doesn't violate the prohibition on territorial claims. it's arguably consistent with the provision about conducting activities for the benefit of all nations, if you squint and interpret national security as a benefit. So, secret satellites remain legal, even if they're philosophically at odds with the treaty's emphasis on transparency and international cooperation. The practical reality is that orbital secrecy is largely theatrical. Any nation with a serious space program can track satellites using military-grade radar and optical systems far more capable than amateur telescopes. When the U.S. moves a classified satellite to a new orbit, China and Russia know about it within days, if not hours. The secrecy is maintained primarily to avoid giving adversaries confirmation about satellite capabilities and to complicate their planning efforts. It's security through obscurity, and like most security through obscurity, it works until it doesn't. None of this is to say that all of orbital space is closed off by political and military considerations. Most of Earth orbit is freely accessible to any nation or company with the resources to reach it. But the exclusion zones are real, even if they're defined more by threat of consequences than by actual barriers. Approach the wrong satellite and you'll face diplomatic protests at minimum, potentially more aggressive responses. Try to occupy an orbital slot that another nation claims and you'll find yourself in a legal and political quagmire. Attempt to land on the moon in a region that another nation has declared a safety zone, and you'll need to navigate a complex web of international relations. These are forbidden zones created not by physics but by politics, and in some ways, they're more difficult to navigate than anything nature has thrown at us. We've covered the places we avoid because of contamination concerns, the regions where radiation and heat make survival impossible, and the zones that politics and military secrecy have placed off limits. But there's one final category of forbidden zones, places where the problem isn't our technology or our treaties, but the fundamental laws of physics themselves. These are regions where our understanding of reality breaks down, where the equations we use to describe the universe start spitting out infinities and nonsense, and where the very concept of going there becomes meaningless. These aren't places we've chosen to avoid, or places where better engineering might someday grant us access. These are places where the universe itself has drawn a line and said, beyond this point, the rules change in ways you cannot imagine. Let's start with the most famous forbidden zone in all of physics, the event horizon of a black hole. Black holes are regions of space-time where gravity has become so intense that nothing, not matter, not light, not information of any kind, can escape once it crosses a boundary called the event horizon. The size of this boundary is determined by the Schwarzschild radius, named after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published his general theory of relativity. For a non-rotating black hole, the Schwarzschild radius is remarkably simple to calculate. Take the mass of the black hole, multiply by 2, multiply by the gravitational constant, and divide by the speed of light squared. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. Compress the entire mass of the Sun into a sphere 3 kilometers in radius, and you've created an event horizon. For a supermassive black hole like the one at the center of our galaxy, which has a mass of about 4 million suns, the Schwarzschild radius is roughly 12 million kilometers, or about 17 times the radius of the Sun itself. The event horizon is a point of no return in the most absolute sense. If you're outside the event horizon, even by a millimeter, you can still escape if you have enough energy. Fire your rockets, achieve escape velocity, and you're free. But once you cross the event horizon, escape becomes not just difficult, but physically impossible. Not because you lack fuel or your engines aren't powerful enough, but because the direction away from the black hole no longer exists in any meaningful sense. Inside the event horizon, all paths through space-time lead inward to the singularity at the center. The future literally points toward the center of the black hole. Trying to escape would be like trying to travel backward in time. It's not a matter of insufficient technology, it's a violation of causality itself. This creates what's known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. The exact quantum state of every particle must be preserved in some form, even if that form is scrambled beyond recognition. But black holes appear to violate this principle. When matter falls into a black hole, all the information about that matter's quantum state appears to be lost forever, hidden behind the event horizon where it can never interact with the outside universe again. Stephen Hawking made this worse in the 1970s by demonstrating that black holes emit radiation due to quantum effects near the event horizon. And over unimaginably long timescales, this Hawking radiation causes black holes to evaporate completely. When the black hole is gone, where did the information go? This paradox has tortured theoretical physicists for decades. Some argue that information is somehow encoded in the Hawking radiation, scrambled but preserved. Others suggest that information is stored at the event horizon itself, in a two-dimensional holographic form. Still others propose that our understanding of quantum mechanics or general relativity must be incomplete. The paradox remains unresolved, which tells you something about how far beyond our understanding black holes really are. But let's set aside the theoretical concerns and ask the practical question. What would happen if you tried to cross an event horizon? The answer depends on the size of the black hole. For a stellar mass black hole, one formed from the collapse of a massive star, the tidal forces near the event horizon are catastrophic. Tidal forces arise because gravity gets stronger as you get closer to a massive object. If you're falling feet first into a black hole, your feet experience stronger gravity than your head. For a stellar mass black hole, this difference becomes extreme very quickly. Long before you reach the event horizon, the force pulling on your feet would be thousands or millions of times stronger than the force pulling on your head. You would be stretched vertically and compressed horizontally, a process that physicists call spaghettification, because apparently they couldn't resist the joke. Your body would be pulled into a long, thin strand, then torn apart at the molecular level, then the atomic level, until you were reduced to a stream of subatomic particles spiraling into the singularity. This would happen well outside the event horizon, so, in principle, a distant observer could watch your destruction through a telescope, though the image would be increasingly redshifted and time dilated as you approached the horizon. For a supermassive black hole, the situation is bizarrely different. Because the event horizon is so much larger, the tidal forces at the horizon are actually quite mild. You could cross the event horizon of a supermassive black hole and, at least initially, feel nothing unusual. You wouldn't notice any particular moment when you crossed the boundary. No alarms would sound, no warning signs would appear. You'd simply be falling, and at some point, you'd realize that the path back had closed behind you. The spaghettification would come later, as you fell deeper and the tidal forces increased. But you'd have time, potentially hours in your reference frame, to contemplate your situation before the end came. So, if you absolutely had to fall into a black hole, you'd want it to be a supermassive one. You'd still die, of course, but at least you'd have time to write a final journal entry or something. From the perspective of an outside observer, though, you'd never quite reach the event horizon. Time dilation near a black hole is so extreme that, as you approached the horizon, time for you would slow down relative to the outside universe. An observer watching you fall would see you move slower and slower, your light increasingly redshifted, until you appeared to freeze just above the event horizon. They'd never see you cross. You'd just fade away as your light was stretched to longer and longer wavelengths. Meanwhile, from your perspective, you'd cross the horizon and reach the singularity in finite time. Both perspectives are correct. This is relativity being weird. The point is that event horizons are absolute barriers. We can theoretically observe black holes from the outside. We've even imaged the glowing accretion disk around one using the Event Horizon Telescope. But we can never retrieve anything that crosses the horizon, can never communicate with it, can never visit it and return. It's the ultimate one-way trip. If black holes represent a barrier we can't cross and survive, neutron stars represent a barrier we can't even approach. Neutron stars are the remnants of massive stars that have exploded as supernovae. When a star, much more massive than the Sun, exhausts its nuclear fuel, its core collapses, and if the core's mass is between about 1.4 and 3 solar masses, it doesn't collapse all the way to a black hole. Instead, it stabilizes as a neutron star, a ball of neutrons packed so tightly that a sugar cube of the material would weigh as much as all of humanity combined. Neutron stars are typically only about 20 kilometers in diameter, roughly the size of a city, but contain more mass than the Sun. The density is so extreme that the protons and electrons in normal matter are crushed together to form neutrons, hence the name. The surface gravity on a neutron star is approximately 200 billion times Earth's gravity. If you somehow managed to place an object on a neutron star's surface, it would weigh 200 billion times what it weighs on Earth. A 1 kilogram object would weigh 200 billion kilograms, more than the mass of Mount Everest. The escape velocity from a neutron star is about half the speed of light. This means that to leave the surface, you would need to accelerate to 150,000 kilometers per second. For comparison, the fastest spacecraft humanity has ever built, the Parker Solar Probe, travels at about 0.05% of light speed. You'd need to be 1,000 times faster just to escape a neutron star. And that's assuming you could survive the other hazards long enough to attempt an escape. The surface temperature of a young neutron star can exceed 1 million degrees Celsius. Older neutron stars cool down, but even after 1 million years, they're still hundreds of thousands of degrees. At these temperatures, any matter approaching the surface would be vaporized instantly, dissociated into a plasma of free nuclei and electrons before it ever touched down. But temperature is the least of your problems. Neutron stars have magnetic fields that make Jupiter's radiation environment look like a gentle massage. The strongest magnetic fields we can create in laboratories on Earth are around a few tens of Teslas. Neutron stars, particularly a subclass called magnetars, can have surface magnetic fields of 10 billion Teslas or more. These magnetic fields are so intense that they distort the quantum vacuum, creating strange effects like vacuum birefringence, where empty space itself becomes birefringent like a crystal. The magnetic fields would rip apart any atoms in their vicinity, stretching them into thin filaments aligned with the field lines. Your body, if it somehow survived long enough to experience this, would be disintegrated at the atomic level not by heat or radiation, but by pure magnetic force. Some neutron stars are also pulsars, rotating at incredible speeds and beaming radiation from their magnetic poles. The fastest known pulsar rotates 716 times per second. That's faster than a kitchen blender. If you were somehow on the surface of this pulsar, you'd experience centrifugal acceleration so extreme that even the intense gravity couldn't hold matter in place. Material on the equator would be flung into space, which is why there's a theoretical maximum rotation rate for neutron stars, beyond which they tear themselves apart. Landing on a neutron star isn't just thermodynamically impossible, it's conceptually incoherent. The very idea of placing a spacecraft or human on such a surface assumes that matter can exist in recognizable form under those conditions, and it cannot. The temperatures, pressures, and magnetic fields would reduce any complex structure to a soup of subatomic particles. You wouldn't land so much as briefly smear yourself across the surface before being absorbed. And even if none of that were a problem, the time dilation near a neutron star is severe. An observer on the surface would experience time about 30% slower than someone far away from any gravitational field. This isn't science fiction speculation. This is measurable gravitational time dilation predicted by general relativity and confirmed by countless experiments. Spend a year on a neutron star, assuming you could, and the rest of the universe would age about 16 months. Black holes have more extreme time dilation, but neutron stars are impressive enough. The point is that neutron stars aren't just hostile environments we might someday engineer our way around. They're regions where the laws of physics as we normally experience them have been cranked to such extremes that matter itself cannot exist in familiar forms. They're forbidden zones not by policy or biology, but by thermodynamics and quantum mechanics. You might think that the sun, familiar old soul that we see every day, would be less of a barrier than exotic objects like black holes and neutron stars. You would be wrong. We've already discussed the Parker Solar Probe's approaches to the solar corona, and how the probe can survive temperatures of millions of degrees because temperature and heat are different things. But there's a limit to how close we can get, and it's determined not by temperature but by density. The corona, the sun's outer atmosphere, is incredibly hot but extremely sparse. As you descend deeper into the sun, the density increases exponentially. The photosphere, the visible surface of the sun, has a density of about 0.0002 grams per cubic centimeter, roughly 1,000th the density of Earth's atmosphere at sea level. That's still pretty sparse. But below the photosphere lies the convective zone, where huge currents of plasma rise and fall, carrying heat from the interior to the surface. Here, the density increases to about 0.1 grams per cubic centimeter, roughly the density of styrofoam. Deeper still, you reach the radiative zone, where energy is transported not by convection, but by photons being absorbed and re-emitted countless times as they slowly, random walk outward. In the radiative zone, the density reaches several grams per cubic centimeter, comparable to water. And at the core, where nuclear fusion converts hydrogen to helium, the density is about 150 grams per cubic centimeter, roughly 13 times the density of lead. The pressure at the core is 265 billion times Earth's atmospheric pressure. The temperature is 15 million degrees Celsius. At these conditions, matter doesn't exist in any solid or liquid form. everything is plasma, nuclei, and electrons moving independently at tremendous speeds. There's no surface to land on because there's no discrete boundary between the different layers. It's just a gradual increase in density and pressure as you descend. A probe trying to enter the Sun would not be crushed or melted. It would be vaporized and ionized, its atoms torn apart and incorporated into the solar plasma. The Parker Solar Probe can skim the corona because the corona is sparse enough that the heat shield can radiate away the small amount of thermal energy it absorbs. But descend deeper into denser layers, and the heat transfer overwhelms any possible shielding. You can't protect against an environment where you're literally surrounded by plasma at millions of degrees. There's no material that remains solid under those conditions, because by definition, solid means atoms in fixed positions, and at solar interior temperatures, atoms don't have fixed positions. They're ionized and moving at substantial fractions of the speed of light. You could theoretically design a probe with active cooling, maybe using magnetic fields to deflect some of the plasma, maybe using ablative shielding that vaporizes to carry heat away. But you're fighting a losing battle. The Sun contains 99.86% of all the mass in the solar system. It's a sphere of plasma held together by its own gravity, generating energy through nuclear fusion. The idea that we could send a probe into that environment and have it survive long enough to transmit data is borderline delusional. Could we at least send something into the convective zone, the outermost layer of the Sun's interior? Maybe. You'd need shielding, capable of withstanding temperatures of a few million degrees and plasma densities comparable to Earth's atmosphere. The technology for this doesn't exist, but it's not obviously impossible. The probe would have a lifespan measured in seconds, maybe minutes if you're wildly optimistic. It would collect data for that brief window and transmit it before being destroyed. Whether the data would be worth the cost of developing and launching such a mission is debatable. We can already study the Sun's interior using helioseismology, analyzing how sound waves propagate through different layers, much like geologists study Earth's interior using seismic waves. A suicidal probe might give us slightly better data, but it's not clear it would revolutionize our understanding. So the interior of the Sun, like the interior of neutron stars and the interiors of black holes, remains fundamentally inaccessible. Not because we haven't tried hard enough, but because the environments are so extreme that matter cannot exist there in any form that could carry and transmit information. Let's shift gears from the impossibly dense to the impossibly distant. Interstellar space, the vast gulf between stars, represents a different kind of barrier. It's not that the environment is hostile. Once you're out of the solar system, space is actually fairly benign aside from the cold and vacuum. The problem is distance. Voyager 1, launched in 1977, is currently the most distant human-made object from Earth. As of late 2024, it's about 24 billion kilometers away, having traveled for nearly 47 years. That sounds impressive until you realize it's only 0.0025 light-years. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. At Voyager 1's current speed, it would take more than 70,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. 70,000 years ago, humans were still living in caves. The pyramids of Egypt are only 4,500 years old. 70,000 years is a time span that exceeds recorded human history by more than an order of magnitude. We're talking about a journey that would span a significant fraction of the time our species has existed. And that's just to reach the nearest star. The Milky Way galaxy is about 100,000 light-years in diameter. At Voyager's speed, crossing the galaxy would take roughly 3 billion years, which is longer than multicellular life has existed on Earth. The tyranny of distance in interstellar space is so overwhelming that it's difficult to grasp emotionally. We're used to thinking of space as something we've conquered. We've been to the moon. We have robots on Mars. We have probes exploring the outer solar system. But all of that is happening within a tiny bubble around the Sun. The solar system, out to the Oort cloud, extends about 2 light-years from the Sun. That's a large region by human standards, but it's nothing compared to interstellar distances. The space between stars is so vast that even light, the fastest thing in the universe, takes years to cross it, and we cannot travel at the speed of light. Current spacecraft travel at a few tens of kilometers per second. Light travels at 300,000 kilometers per second. We're off by a factor of 10,000. Proposals exist for faster spacecraft. The Breakthrough Starshot Initiative, funded by billionaire Yuri Milner, envisions tiny probes propelled by powerful lasers to speeds of up to 20% of light speed. At that velocity, a probe could reach Proxima Centauri in about 20 years. The technology is wildly speculative, requiring lasers far more powerful than anything we've built and light sails far more advanced than we can currently manufacture. But it's not obviously impossible. The bigger problem is that at 20% of light speed, collisions with interstellar dust become catastrophic. Space between stars isn't perfectly empty. There are about 1 million hydrogen atoms per cubic meter in the interstellar medium, along with occasional dust grains. At low speeds, these particles are harmless, but at relativistic speeds, they become deadly projectiles. A dust grain massing 1 microgram, about the mass of a grain of sand, impacting a spacecraft traveling at 20% of light speed, would release energy equivalent to detonating about 10 kilograms of TNT. That's enough to obliterate any probe we could build. You would need shielding, probably some form of magnetic field to deflect charged particles, and a sacrificial forward layer to absorb impacts from neutral particles. This adds mass, which makes acceleration harder, which requires more laser power, which increases cost. The engineering challenges cascade, and even if you solve all of them, you're still looking at a 20-year journey to the nearest star, followed by another 4.2 years for the signal to get back to Earth. A round-trip communication takes nearly a decade. The people who designed and launched the mission will likely be retired or dead by the time the data arrives. And that's for the nearest star. Most stars are much farther away. The median distance between stars in our region of the galaxy is about 5 light-years. If you pick a random star, odds are it's much farther than Proxima Centauri. Interstellar space isn't forbidden in the sense that we're prohibited from crossing it. It's forbidden in the sense that the distances are so staggering that meaningful exploration may be functionally impossible for any civilization that hasn't learned to extend its own lifespan or build multi-generational vessels. We're not talking about a technological barrier we might overcome with better rockets. We're talking about a fundamental constraint imposed by the size of the universe and the speed of light. And if interstellar space is daunting, intergalactic space is literally unreachable. The observable universe extends about 46.5 billion light-years in every direction from Earth. This is larger than 13.8 billion light-years, the age of the universe in years, because the universe has been expanding during the time light has been traveling toward us. The edge of the observable universe isn't a physical barrier, it's an informational one. Beyond that distance, light hasn't had time to reach us since the Big Bang. We cannot see beyond it, and we never will. But it gets worse. Due to the accelerating expansion of the universe driven by dark energy, distant galaxies are receding from us faster than light. Not moving through space faster than light, which is prohibited by relativity, but being carried away by the expansion of space itself, which has no speed limit. Galaxies beyond a certain distance, currently about 15 billion light-years, are receding so fast that light leaving our galaxy now will never reach them. Even if we sent a signal at light speed, it would never catch up to those galaxies. They are fundamentally unreachable, and the boundary of reachability is shrinking. Every year, galaxies cross the threshold from theoretically reachable to forever inaccessible. In the very far future, trillions of years from now, our local group of galaxies will be completely isolated. Everything outside our gravitationally bound cluster will have been carried beyond the cosmic horizon. Future astronomers in that era, assuming anyone still exists, will look out and see almost nothing. No distant galaxies, no cosmic microwave background, just a handful of nearby galaxies and a vast, empty darkness. They will have no evidence that the universe is expanding or that a Big Bang ever occurred. The observable universe will shrink to just our local neighborhood, and everything we know about cosmology will be lost, erased by the universe's expansion. This is the ultimate exclusion zone, the unreachable everything beyond a horizon determined not by human decisions or hostile environments, but by the fundamental expansion of space-time. And even if we could somehow travel faster than light, which we can't, there would still be limits. At extremely small scales, quantum mechanics and general relativity come into conflict, and our understanding of physics breaks down completely. This happens at the Planck scale, distances of about 1.6 times 10 to the negative 35 meters, and timescales of about 5 times 10 to the negative 44 seconds. At the Planck scale, quantum fluctuations in spacetime become so large that the very concept of smooth, continuous space breaks down. Spacetime becomes a roiling foam of quantum uncertainties, sometimes called quantum foam, where cause and effect lose meaning and particles can spontaneously appear and disappear. Our equations, both quantum mechanics and general relativity, produce infinities and nonsense when applied. To the Planck scale, this isn't because the equations are wrong exactly. They're spectacularly successful at describing everything we can observe. But they're incomplete. They don't account for a quantum theory of gravity, and at the Planck scale, gravity becomes just as important as quantum effects. String theory and loop quantum gravity are attempts to describe physics at the Planck scale, but they're highly speculative and lack experimental evidence. We cannot build particle accelerators powerful enough to probe Planck scale energies. The energy required is about 10 to the 19 giga electron volts, roughly the energy of a speeding car compressed into a single subatomic particle. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 10 tera-electron volts, which is impressive until you realize it's still 15 orders of magnitude short of Planck scale energies. We're not even close. We're not in the same galaxy of close. This means that the Planck scale represents a fundamental limit to our knowledge. We cannot observe it directly. We can only theorize and hope that indirect evidence might constrain our models. There might be phenomena that occur at the Planck scale that are in principle unobservable, unknowable, beyond the reach of any experiment we could ever conduct. And if that's true, then we've hit a boundary not just on where we can go, but on what we can know. The universe might contain regions, or scales, or phenomena that are forever hidden from us not by distance or politics, but by the nature of reality itself. It's a sobering thought. For all our technological progress, for all our scientific understanding, there may be aspects of the universe that we will never be able to access or comprehend. Some boundaries cannot be crossed because they're not really boundaries at all. They're limits to the applicability of the concepts we use to describe the world. So where does this leave us? We've covered a lot of forbidden zones, from the special regions on Mars where we're forbidden to land lest we contaminate potential alien life, to the Van Allen radiation belts that fry electronics and kill humans, to the political exclusion zones around military satellites, to the event horizons of black holes where physics becomes so extreme that escape is impossible, to the ever-expanding cosmic horizon beyond which galaxies are forever unreachable. These barriers fall into roughly 3 categories. First, there are the boundaries we've imposed on ourselves, the planetary protection protocols and political restrictions. These are barriers of choice, and in principle, we could change them any time. Whether we should is a separate question. Second, there are the boundaries imposed by current technology, the radiation environments we can't yet shield against, the temperatures we can't yet survive, the distances we can't yet cross in reasonable time frames. These are barriers of capability. Better, engineering might overcome them or might not. We won't know until we try. Third, there are the boundaries imposed by physics itself, the event horizons we cannot cross and return from, the Planck scale we cannot observe, the distant galaxies we cannot reach because space itself is expanding too quickly. These are absolute barriers. No amount of clever engineering will let us visit the interior of a black hole and come back to tell about it. No breakthrough in propulsion will let us travel faster than the expansion of the universe. These limits are built into the structure of reality. The distinction between cannot and should not is crucial. We cannot cross an event horizon and survive. We should not contaminate Mars with Earth bacteria before we've determined whether Martian life exists. The first is a statement about physics. The second is a statement about ethics. Conflating the two leads to poor decisions. It's worth noting that throughout history, boundaries have driven innovation. The METI debate, the question of whether we should transmit messages to potential aliens, has pushed us to develop better transmission technology, more sophisticated encoding schemes, and deeper thinking about what makes a message comprehensible to non-human intelligences. The planetary protection requirements have driven advances in sterilization techniques and cleanroom protocols that have applications far beyond space exploration. The challenge of surviving Jupiter's radiation environment has led to better shielding designs and more radiation-hardened electronics. Boundaries don't just restrict us, they focus our efforts and force us to be creative. The philosophical question is whether we should respect these boundaries or push against them. The cautious answer is that we should respect boundaries when the consequences of crossing them are severe and irreversible. Contaminating an alien biosphere, if one exists, would be an irreplaceable loss. Starting a war over a satellite proximity operation would be catastrophic. These are cases where caution is justified. But we should push against boundaries when the potential benefits outweigh the risks, and when the boundaries are based more on fear than on evidence. The prohibition on landing near Mars' RSL features might have made sense when we thought they were briny water, but if they're actually just dust avalanches, the restriction is pointless. The fear of METI might be overblown if the odds of actually contacting aliens are as vanishingly small as they appear to be. And the boundaries imposed by current technology are absolutely worth pushing. We should try to develop better radiation shielding, faster propulsion, more capable spacecraft. The fact that interstellar travel seems impossibly difficult with current technology doesn't mean it will always be so. A century and a half ago, powered flight seemed impossible. A century ago, reaching the moon seemed like pure fantasy. 50 years ago, landing on Mars with a functioning rover seemed extraordinarily difficult, and now we've done it multiple times. Today's impossibilities become tomorrow's accomplishments, not always, but often enough that dismissing challenges as impossible is premature. The universe, in a sense, has its own planetary protection protocol. It's called physics. The places that would be most dangerous for us to contaminate, the interiors of stars, the event horizons of black holes, the quantum foam at the Planck scale, are also the places where physics makes it impossible for us to go. We couldn't contaminate the interior of a neutron star even if we wanted to, because nothing we send there would survive long enough to make a difference. The universe protects itself through temperature, pressure, and space-time curvature. We only need to protect the places where survival is possible, and even then, only until we know enough to make informed decisions. So, yes, there are forbidden zones throughout space, regions we cannot or should not visit. But the map is not static. As our knowledge grows and our technology improves, some boundaries will shift. Others will remain fixed, carved into reality by the laws of physics themselves. And that's okay. The universe is large enough, strange enough, and wonderful enough that even with all these restrictions, we have more than enough to explore for the foreseeable future. The forbidden zones don't limit us so much as they define the shape of what's possible, and in doing so, they make the possible more precious.